Because of the strong nuclear force, the nucleons in a stable nucleus are held tightly together. Therefore, energy is required to separate a stable nucleus into its constituent protons and neutrons, as the figure illustrates. The more stable the nucleus, the greater the amount of energy required to break it apart. The required energy is called the binding energy of the nucleus. We encountered a similar situation in our study of atomic structure in the photoelectric effect. There, we observed that a minimum amount of energy was required to remove an electron bound to an atom in a metal. This binding energy of the electron to the metal was called the work function. Its typical value was a few electron volts. We will see that the nuclear binding energy is millions of times greater. In Chapter 28, Einstein showed that mass and energy are equivalent. In fact, the rest energy, E0, and the mass m are related by his famous rest mass equation, E0 equals mc squared, where c is the speed of light in a vacuum. Therefore, a change in the rest energy, delta E0 of a system, is equivalent to a change in mass, delta m, according to the following. We see then that the binding energy used in the figure to hold the nucleus together appears as extra mass in the separated and stationary nucleons. In other words, the sum of the individual masses of the separated protons and neutrons is greater by an amount delta m than the mass of the stable nucleus itself. This difference in mass, delta m, is known as the mass defect of the nucleus. The binding energy of a nucleus can be determined by the mass defect using Einstein's rest mass equation. Binding energy equals mass defect times c squared. To calculate the binding energy of a particular nucleus, we must first find its mass defect. The mass defect will be equal to the difference in the sum of the masses of the separated protons and neutrons minus the mass of the nucleus. Sometimes the mass of the nucleus will be given in kilograms. However, more frequently, the binding energy of a nucleus is found by using the atomic mass. It is customary to use the atomic mass unit, U, instead of the kilogram. As introduced in section 14.1, the atomic mass unit is 1/12 of the mass of a carbon-12 atom. In terms of this unit, the mass of carbon-12 is exactly 12U. The following table also gives the masses of the electron, the proton, and the neutron in atomic mass units. For future calculations, the energy equivalent of one atomic mass unit can be determined by observing that the mass of a proton is 1.6726 times 10 to the minus 27 kilograms, or 1.0073 U, so that 1 U is equal to 1.6605 times 10 to the minus 27 kilograms, and delta E0 is equal to 1.4924 times 10 to the minus 10 joules. In electron volts, therefore, one atomic mass unit is equivalent to 931.5 mega electron volts. Data tables for isotopes, such as the table in Appendix F, give masses in atomic mass units, that is, the masses of neutral atoms including the mass of the orbital electrons. When using atomic masses to calculate nuclear binding energies, we must again find the mass defect. However, instead of separating the nucleus into individual protons and neutrons, we separate the atom into individual hydrogen atoms and neutrons. This takes into account the mass of the orbital electrons. The mass defect will then be equal to the difference in the sum of the masses of individual hydrogen atoms and neutrons minus the atomic mass. This will give us the mass defect in atomic mass units. We can use the equivalent relation that one atomic mass unit is equivalent to 931.5 MeV of binding energy. Multiplying the mass defect by 931.5 MeV gives us the nuclear binding energy. To see how the nuclear binding energy varies from nucleus to nucleus, it is necessary to compare the binding energy for each nucleus on a per-nucleon basis. The following graph shows a plot in which the binding energy divided by the nucleon number A is plotted against the nucleon number itself. In the graph, the peak for the helium-4 isotope indicates that its nucleus is particularly stable. The binding energy per nucleon increases rapidly for nuclei with small masses and reaches a maximum of about 8.7 MeV per nucleon for a nucleon number of about A equals 60. For greater nucleon numbers, the binding energy per nucleon decreases gradually. Eventually, the binding energy per nucleon decreases enough so there is insufficient binding energy to hold the nucleus together. Nuclei more massive than bismuth-209 are unstable and hence radioactive.